Good morning, everyone. It's a great pleasure to be here and entertain you with some of our ongoing work at Penn State on the extraction of the critical minerals from primary and secondary sources, especially acid mine drainage. We had two outstanding presentations by Dr. Kruwata and Dr. Day-Lewis, and I personally have been benefited with a lot of publications with Dr. Kruwata, so it's great to be here and build upon his presentation and then further explain our work. So before starting, I'd like to acknowledge my research team members and also sponsors and collaborators for putting these works together. So on the critical minerals, you're already familiar with them. So U.S. Department of Interior has listed 50 minerals and elements as the critical minerals. And among them, U.S. is heavily reliant on the foreign sources for them. So for the 12 of them, 100% import reliance, and also for the 20 over 20 for the another 29 of them over 50% import reliance, and among them also 17 rare earth elements, including 15 lanthanides and scandium and yttrium. And this map shows the point sources of the import of these elements. As you can see, like the top countries for the those critical mineral source point of the import are China and Canada, and there has been a lot of restriction and bans on the export of those critical minerals recently. That causes a lot of interruption in the supply chains for the critical minerals that they have. These critical minerals have a lot of application in supply chains, including critical minerals and materials like rare earth magnets that have application in a lot of high-tech industry, lithium-ion battery supply chain, semiconductor supply chain, and new energy and renewable sources, for example, solar panels. We also have a lot of these critical minerals, including rubidium and cesium, that now with the export bans, they are suffering with the supply chain for the production. And among the for the rare earth elements, as you can see, China is the top producer of the rare earth elements, and also a lot of other sources from the other countries end up to the China for the final separation and then exported from China as well. And U.S. only has one mine, Mountain Pass in California, that is operating, and is mostly, so they are operating bastnasite, and then they are producing light rare earth elements and focus on the NdPr, niobium, and praseodymium, and they are but closing the loop for the rare earth magnet. So as you can see, so there are a lot of needs for the extraction of these critical minerals from other viable sources. So we need to take a look at all potential sources, including the secondary sources. And Penn State has a longest history on the extraction of the critical minerals from different sources. As you can see, at 1952, Dr. Steidel, one of our previous deans of the college, said by the year of 2000, we will not be wasting our coal ash, in which geochemists have shown that there is a notable concentration of the rare earth elements, such as germanium and rare earth. We will be recovering these elements. And we are a lot of research are focusing on this area nowadays, and some of the secondary sources, including the mine waste and urban waste, including the waste of the heavy mineral sand, red mud, which is the waste of the aluminum production, clay waste for the phosphate, oil shale, and produced water, then also iron and copper waste, coal waste, both of the coal mine, coal tailing, and also fly ash and bottom ash for the, as some of the potential sources, geothermal brine that we have in California, for example, and then another one is acid mine drainage. And on top of those ones, some of the other sources are like recycling of the material electronic waste and solar panels. So these are some of the secondary sources that we are conducting research for the extraction of the critical minerals from them at Penn State. And specifically today regarding the acid mine drainage, some of the work that we have done, I'll cover it and then update you on where we are right now. So acid mine drainage, so you're already familiar with that one through the presentation of Dr. Crowato. So in the sulfide minerals and also coal, so pyrite is one of the major gangue minerals that is concentrated in the waste streams and coal refuse piles. And pyrite in presence of the oxygen and water is oxidized and generate ferrous ions, sulfate ions, and hydrogen ions. Then this ferrous ion, again in presence of the oxygen and water, will be converted to the ferric, and then from there, ferric will be acting as the oxidizer for the pyrite, and then without even the presence of the oxygen, pyrite will be oxidized and generate again ferrous, and then even higher acidity in the solution. So then, and this loop will be continue and then continuously generating acid mine drainage and releasing hydrogen ions in the leachate. So in that low pH and in the pH and EH conditions of the acid mine drainage, so majority of the major elements and trace elements are solubilized. So as you can see, the solubility region for a lot of these elements. So, and then that acid mine drainage can dissolve majority of the critical minerals, major elements, and also trace elements. And acid mine drainage has been of environmental concern for decades and is one of the concerns globally, nationally, and also in our region. In Pennsylvania, we have more than 5,500 miles of the water stream contaminated by acid mine drainage. And at the same time, that it poses a lot of challenges and needs to be treated for the environmental compliance and requires a lot of cost for the treatment of those one. The recent study has shown that the acid mine drainage can selectively dissolve heavy rare earth elements. And at the same time, another study by our colleague at WVU showed that 700 to 3,400 of the per ton of the rare earth elements can be recovered from the AMD in the Appalachian basin. So if we can selectively recover these critical minerals while we are treating acid mine drainage, it can significantly enhance the sustainability of the process. And we can take a look at the acid mine drainage rather than a challenge and opportunity. So here is the typical active treatment process for the treatment of the acid mine drainage. So then acid mine drainage is collected in the ponds, treatment ponds, and then through the treatment ponds, typically it's been treated with the caustic treatment by addition of the lime or sodium hydroxide, and then so the pH will be adjusted to around circumneutral pH, and majority of the elements that were dissolved in the acid mine drainage now precipitated out from the acid mine drainage, and the precipitated material that are called sludge will be pumped out in the sludge ponds, and they will be dry out or can be filtered through different filtration units, jaw tubes or centrifuge tubes, and then the discharged water, the treated water can be discharged to the environment. So both of the acid mine drainage and sludge material have shown that they have contain elevated content of the critical minerals. And for the, so as sludge also same thing, but the issue with the extraction of the critical mineral from sludge is that it requires significant amount of the acid to bring it back into the solution and again separating those critical minerals. So while they are in the acid mine drainage, if we can change the process or modify the process while we are treating it for the environmental compliance, at the same time recover those critical minerals selectively, that would be the more appropriate approach than going after the sludge, at least economically. So some of the sites that we have characterized show that, again, it contained both of the sludge and acid mine drainage, show that they have elevated content of the rare earth elements, and then so they have also higher heavy to light ratio of the rare earth elements. That it's very important in the resource assessment, because even the mine that we have at Mountain Pass in California has mostly mined for the light rare earth elements, and then acid mine drainage can provide heavy rare earth elements for the supply chain of the critical mineral in the US. So here are the treatments, the sites that we collected the samples. So as you can see, again, we have the treatment ponds and then settling ponds and then the sludge pond. That's the first site. The second site, again, same thing. Treatment and settling pond and sludge ponds. Same thing again for the third pond. So that's the AMD river coming over here, and then that's the treatment pond, and then settling pond, and then the sludge ponds over here, as you can see. And there are a lot of these sites close to each other nearby that as we extract critical minerals from different sites, so there could be a central facility for purification of those critical minerals as well. So in order to figure out best approaches for the selectively separating those critical minerals from acid mine drainage, we took a look at the behavior of the precipitation of the rare earth elements throughout the treatment process. So we conducted a stage precipitation by incrementally adjusting the pH to the different values using the different chemicals that can potentially be used for the AMD treatment or recovery of these minerals. So rather than going all the way to the pH 7, so we went to the pH incrementally one by one, and then we analyzed this precipitated material to figure out how is the behavior of the precipitation of the rare earth elements. So we took a look at the different ligands, so hydroxide treatment, carbonate treatment, phosphate treatment, ammonia treatment, and as you can see, the bases, so you see that a lot of hydroxide treatment is the conventional method, so it's using sodium hydroxide or lime. So what we found that for the extraction of the rare earth elements through the hydroxide treatment, it requires the elevated pH more than 9, and the recovery is still limited to about 85%. But as we are doing the carbonate precipitation, such as using the sodium carbonate, soda ash, so it has a lot of benefits similar to the phosphate precipitation, but phosphate cannot be used for the AMD treatment, so we focus on the carbonate treatment using the soda ash. So as you can see, if you compare the red lines, recovery lines from the hydroxide treatment with the carbonate treatment, so not only the amount of the recovery has been increased through the carbonate precipitation, but at the same time, it brings the maximum precipitation pH from the pH 9 to about pH 7. So majority of the rare earth elements now can be precipitated below pH 7. That is the target pH treatment for the acid mine drainage, and that's because of the lower Gibbs free energy of the formation of the carbonate and lower solubility product of the carbonate formation of the rare earth elements than hydroxide formation. So it has advantages in terms of the maximizing rare earth elements recovery, and we took a look at it then later for the other major elements such as the iron and aluminum that can be a contaminants or can be diluting the grade of these rare earth elements in the precipitate. So we took a look at it, also the precipitation behavior of the other elements, such as major one is aluminum. So we found that through this process, there is a window of the separation for the aluminum and rare earth elements, and separation of those ones during the treatment process would be very important and very significant in reducing the cost for the downstream purification processes, because the rare earth elements and aluminum, both of them are trivalent, and if we can separate them at least get a higher concentration or removal of the aluminum from rare earth elements, it reduces the cost of the downstream purification processes. So as you can see over here, up to pH 5, we can remove more than 90% of our aluminum with minimal loss of the rare earth elements at the aluminum precipitate. And then in the second stage, we can go to the second stage for the extraction of the rare earth elements by going to the pH 7. So we propose the two-stage carbonate precipitation process first, And as you can see, through the first stage, we can recover about more than 90% of the aluminum at the pH 5, and then we go through the pH 7, and we recovered more than 85% of the rare earth elements. And I would be happy to share our paper and publication if you are interested in those work. And also we take a look at our CO2 mineralization process. If there are locations that the CO2 is available as a source of the carbonate for the precipitation, we took a look at the CO2 mineralization as well. And then again, CO2 mineralization could provide the carbonate ligands, and we saw the similar trend as the soda ash. And also it's same behavior that we could go with the two-stage carbonate precipitation process, that in the first stage, again, we remove the aluminum up to pH 5. And then in the second stage, we recover our rare earth elements by going to the second pond at pH 7. And also that result had been published. And then we further modified the process to a 3-stage, one pre-treatment stage, that the iron can be aerated through a lot of technologies that are available, such as Mastrom by the Somerset International Company in Pennsylvania, that it aerate, and as Dr. Kowat also mentioned, that it can aerate the acid mine drainage and then oxidize iron, and then iron can be precipitated in the first pond at pH around 4, then second pond using the carbonate precipitation at pH 5, we get the cake or concentrate of the aluminum, and then in the last pond, the rare earth elements. So a stage precipitation process for selective recovery of some of these critical minerals. That's what we developed, and then we further took a look at the kinetic of the precipitation of the different stage of the precipitation, including nucleation, growth, ripening, and aggregation of those one. And happy to collaborate on share all the data that we have and collaborate with for the comparison of the studies of the modeling studies that are available, again, through the FreakN model. And again, we conducted those kinetic studies mainly for the obtaining scale-up processes, for the scale-up R process, going for the lab scale to the pilot scale study, and then validate those results, and then conducting the field demonstration. And we further took a look at the purification processes. So again, in our process at the pH 4, through the aeration, iron can be precipitated at pH 5. Aluminum using carbonate can be precipitated. So the aluminum grade that we get at this stage is about 15 to 20% purity. So for the purification of the aluminum, what we did, we simulated the process that is being used in the bauxite processing for the aluminum production. So we went through the elevated pH at pH 12 by addition of the sodium hydroxide, so redissolving the precipitated materials. That majority of the contamination of that one is iron, and then using the CO2 purging, the pH will be reduced to 9, and then we get a high purity cake of the aluminum. For the rare earth elements, the majority of the research that has been performed are using the solvent extraction. That is a costly process, and there are some environmental concerns regarding that process, and it takes a lot of stages for the purification. So rather than using the solvent extraction processes, so we propose to utilize the stage carbonate precipitation again. So the rare earth elements grade that we get at the pond first treatment through the treatment process is about 2%. So we take this cake and we redissolve it at the pH 2, and then we repeat this process. So any carryover of the aluminum that are left over here, that 10%, so we can again precipitate it at pH 5, and then get a more pure cake of rare earth elements, and then we can go again, repeat that process, and again another 10%, any 10% of that one that is left of the aluminum, again we precipitate it, and at the end we get the high purity cake of the rare earth mixed rare earth oxide or carbonate, and that can be calcined and then turn it to the oxide. And then I'll explain our work on the transition critical minerals, including cobalt, nickel, manganese recovery in next slide as well. So we further characterized our product that obtained through our purification process. And as you can see, this is our cake of the final product of the aluminum, rare earth elements, and cobalt, nickel, manganese cake. And we were able to obtain through our process more than 90% purity of the aluminum product in terms of the boehmite and dawsonite. And then our rare earth elements, we got a purity of the 88.5% that we can calcine it in terms of the rare earth carbonate or sodium rare earth carbonate, that we can calcine it and then get more than 90% in terms of the oxide as well. And then we got a relatively high quality of the manganese oxide and cobalt oxide that we are further modifying our process to increase the purity of the cobalt and manganese as well. And again, our purification process has been published. I'm happy to share that one as well. So right now we are at pH 7, but there are still some transition critical minerals that are available in acid mine drainage, and including manganese, and there are a lot of more restriction for the treatment of the acid mine drainage for the manganese. So for the manganese now in our process, we are about pH 7. For the transition critical minerals, there are multiple approaches for precipitation of those ones. So you can either go horizontally in per Bay diagrams than by increasing the pH. That requires about pH more than 9 for the precipitation of the manganese or cobalt or nickel. Or you can go vertically up to the solid phases of the precipitation by using the oxidants such as permanganate, potassium permanganate, or other oxidants. So these are multiple approaches that can be taken. So for example, in some of the sites that we visited, they go all the way to the pH 9.5, 10 to precipitate manganese, and at the end, for the discharge, they add citric acid to bring it back to the pH 7 so they can discharge it. Or in some sites, so we saw that they are using the strong oxidants such as potassium permanganate and other oxidants. Same as for the nickel or other transition critical minerals. So we took a look at it, that how we can address that challenges of to avoid going for the high pH or avoid using the costly oxidant to precipitate those one from the acid mine drainage. What we did on those one, again, we studied the effect of the ligands or different type of the oxidants for the precipitation of the transition critical minerals such as cobalt, nickel, manganese. And again, we took a look at the different ligands and different oxidants, including potassium permanganate, sodium persulfate, and ozone. And what we found that for the transition critical mineral precipitation among the different ligands, so ammonia was the most effective one, but at the elevated pH around 9.5, that recovered more than 95% of the manganese. But again, the pH should be adjusted back to the circumneutral for the discharge. And then among all the oxidants that we tested, so ozone resulted in the highest recovery and grade of the cobalt, nickel, and manganese in the precipitates at the circumneutral pH. So at the pH 7, we could, by purging the ozone in the system, we could precipitate those cobalt, nickel, manganese from the acid mine drainage as well. So then we got a relatively high purity cake of the manganese, cobalt, and nickel. And then the reason that we picked the ozone is that, first of all, it has among the oxidizing reagent that has high oxidation potential and can be reduced, doesn't introduce impurities into the solution. And that can be generated on the site, but still we need to do the techno-economic analysis to performing that one. So as the recap, our process is the stage precipitation process. First stage, we go through the aeration, through the available technologies, maelstrom, and then we elevated the pH to pH 4 for the recovery of the iron. Then we go to the carbonate precipitation by addition of the soda ash. At pH 5, we get our aluminum recovery. Then we go to the pH 7, third pond, for the rare earth elements recovery. And at the pH 7, after we recovered our rare earth elements, we inject ozone and purge ozone into the acid mine drainer, and we recover the transition critical minerals, including manganese, and then we subjected those the cake or precipitates to our purification process to get the high purity critical minerals streams. And we merge those two patented processes through the scale-up parameters that we performed through the kinetic studies. First, we conducted from the lab scale data, we conducted bench scale continuous operation, and now we are in the process of the building 10,000 gallon per day pilot facility, and that's going to be live and operational in a couple of months, and we would be happy to host you for the visit anytime that you like. Just contact me, and we would be, if you are in the State College area, and we would be happy to walk you through our process, our lab, and show you our facility as well. So through this process, we would conduct also TA, LCA of the process, techno-economic assessment, life cycle assessment, and then validate some of our scale-up parameters to going for the next stage of the demonstration. And at the same time, we have been collaborating with the industry partners. We recently got another funding from the Department of the Energy that while we are extracting the critical minerals, including the aluminum, rare earth elements, cobalt, nickel, manganese from the acid mine drainage, and lithium and titanium from the Mercer clay sources. So those, what we obtain in our process is mixed rare earth oxide. So then we send it to our partner company, Rare Earth Salt, so they separate it and then generate the 4,9 purity of the individual rare earth oxide. And then another company, Aquametal, also increase the purity of the cobalt, nickel, manganese, separated to 4,9 purity. And then those separated rare earth elements and cobalt, will be provided to the GE Aerospace, and GE Aerospace is taking a look at it from this product obtained from the coal waste sources to make alloys, super alloys, and magnets. And then at the end, they also conduct a complete TA, LCA of the integrated process to close the loop of the supply chain within the US to go from the waste streams to defense applications. And with that, I appreciate your attention. Thank you so much.